All right, moving right along, we are going to get into section 1.2 today. And section 1.2 is going to continue down our path of exploring some more basic facts of geometry. And before we can get started, we must first define a couple of things, like always, and say that a rule that is accepted as truth, so anything that you say that this is true because it's true, is going to be called a postulate. And if you have a rule that must be proven, so a rule that you prove is called a theorem. So in mathematics, there is some things that are just given to be true. Like the way that we have set up numbers 2 plus 2 equaling 4 is just a truth, right? But there's other things in mathematics that they look true, but you don't know they're true. So you have to prove to somebody else that they're true. We'll get into theorems much later, but today we're going to do our first postulate, and this is going to be postulate 1.1. And it's a very, very basic postulate, just to introduce the idea. It is the Euler postulate. And now the Euler postulate is basically saying that the distance between 2 points can be measured. So the distance between points A and B written AB. So if you ever see something that looks like it should be like a line or a segment or array, and you just see A and B with nothing above it, that means the distance or the length of AB is going to be absolute value difference between the two. So that makes sense, right? If we go ahead and draw ourselves a line segment here, and we're going to call this line segment AB, and say we put AB on the coordinate plane, right? And this is at some point x1, and B is at some point x2, then the length from A to B is going to be the difference, the absolute value of x1 minus x2. We want the absolute value because there's no negative lengths. You can't say this is negative 5 feet long. That just doesn't make a whole lot of sense. And if you have two segments that are the same length, those are going to be called congruent segments. So congruent segments are line segments with the same length. All right, you would draw these out like so. So if we have this line segment right here as AB, and this line segment right here as CD, we would say that AB, the line segment AB, is congruent to the line segment CD. And that is really long to write out, so mathematics likes to shorten something, so we use this equal sign in between the two with a squiggly above it. And so we would say AB is congruent to CD. Line segment AB is congruent to line segment CD. So their lengths are equal and the segments are also equal. And to identify congruent segments on the segment themselves, if you ever see a red tick, that means these two are congruent. Now, if I were to draw another two segments, say these two right here, E, F, and G and H, notice that EF and GH are also congruent to one another, but they're not congruent to AB. So these double ticks means that those two are congruent, and the two singular ticks mean that the other two are congruent. And our first example today is going to see if two segments are congruent. So if we draw here in the coordinate plane, and now bear with me, every time I draw a coordinate plane, I'm not drawing it perfect. I could always, import a picture of the coordinate plane, but that takes time, and quite frankly, I find a benefit in being able to quickly draw a relatively accurate coordinate plane. And normally you just have to go to about 5 positions on the x and y axis. So if we put a point here at -3, +4, and call that J, and we put another point over here and call it 2, 4, and call that K, and then connect those two with a line, that is going to be the line segment JK. And if we put another point here, L, at the point 1, 3, oops, I just realized that I put both of these at 5, so that's okay. We can say 2, 5 and -3, 5. All right, and we put another point here at 1, 3, and we're going to call that one L. And we put another one here at 1, -2, and call that M. We connect those two with a line segment. Notice that I'm not exactly there at 1. That's okay. This is just an example. I'm going to ask the question, is JK, the line segment JK, congruent to the line segment LM? And so we have to find the length of each one of these segments. Notice here that when we go from J to K, we stay at an elevation of 5. So the only thing that is changing is our x coordinate. We go from a -3 to a 2. So to first find the length of JK, we will take our ruler postulate and then take the absolute value of our -3 minus our 2. We're literally just counting the squares. 1, 2, 3, 4, 5. -3 minus 2 is equal to a -5, and the absolute value of a -5 is 5. We can do the same exact thing for LM, but notice now it's not our x position that is changing, it is our y position that is changing. So we're going to take a +3 minus a -2, +3 minus a -2. That's like plussing, so that's going to be equal to a +5, and the absolute value of a +5 is a +5. So since JK is equal to 5, which is also equal to LM, we would say that the line segment JK is congruent to the line segment LM. All right, moving right along, if we draw a couple more lines over here and put 3 points on this line, let's say we have A, B, and C, we would say that point B, and we can label that like that, is between points A and C. And if we draw another line over here and then put on it D and F, and then put point E over here, we would say that point E is not between D and F. So for a point to be between means that it is on the same line. It's collinear with those points, right? We have to go out of our way and make a triangle to get to E. But from A to B to C is one straight line. And so our second postulate is going to deal with this between concept. So postulate 1.2 is going to state the following. If B is between A and C, then AB plus BC is equal to AC. That makes sense. You can add segments. And so this postulate is going to be called the segment addition postulate. And likewise, if AB plus BC equals AC, then B is between A and C. And so if we draw a line out right here and put on it the points A, B, and C, and then we measure the distance from A to B, we call that AB, and we also measure the distance from B to C, and call that BC, we can add those two together to get the entire distance of AC. So AB plus the length of BC is equal to the length of AC. And so now we can apply that to an example. So if we draw a line right here and put on it the points D, E, and F, and we label DE as 23 and EF as 35, I want to find the total length of DF. So DF is going to be equal to the length of D to E plus the length of E to F. And so that is going to be equal to 23 plus 35, which is going to be equal to 58 units. So 58 is equal to DF. Next example, I want to take a line here, and we're going to put on this guy F, G, and H. And we are given that the entire length from F to H is equal to 36 units. But the length from F to G is only equal to 21 units, and I want to find the length of GH. So we want to find this missing piece right there. So we know that the entire length FH is going to be equal to the two smaller lengths added together, FG plus GH. So if we plug in the numbers that we do know, FH is equal to 36, FG is equal to 21, and GH is equal to, well, GH, it's our unknown. We can use simple algebraic inverse operations to solve for GH. So we'll subtract 21 from both sides. And 36 minus 21 is 15, so 15 is equal to GH. That is all I got for you today. That is section 1.2. Thank you for watching, and I'll see you in the next one.